Let's say you wanted to estimate how readily hemoglobin will give up its bound oxygen molecule under particular conditions. To estimate this, we can consider the reaction, the elementary reaction. A bound hemoglobin with an oxygen molecule has a forward and a reverse reaction in which it dissociates into unbound hemoglobin and an O2 molecule. And this is a simplification because in reality hemoglobin can bind multiple oxygen molecules, but for the sake of keeping things simple to understand the concepts involved, we'll assume this model. And this is actually a common chemical engineering problem we face in practice. How do you estimate rate laws from data? And to start off with, we're going to need to have or propose an elementary reaction and see if it agrees with the data that we obtain experimentally to draw any conclusions. And so in this example, what we are going to be doing is estimate the reaction order and rate constant from data that we obtained in an experiment on hemoglobin as it's giving up its oxygen molecule using a tubular or also plug flow reactor. It's synonymous. In this experiment, what happened is we had a plug flow reactor with an initial volumetric inlet flow rate of 19.6 cubic centimeters per second with pure, or not pure, but it had a known concentration of 2.33 times 10 to the minus 6 moles of bound hemoglobin per cubic centimeter. And we know along each point that are equidistant in the plug flow reactor what percentage of the bound hemoglobin decomposed. So we have this data, and what we would like to extract from this data is a rate constant and figure out what order the reaction is. Is it first order, second order, zeroth order, negative order? We don't know. So we have to turn to data analysis to derive this information. And what we use are things referred to as differential reactors. A differential reactor operates at a very low conversion, very close to zero, but it can range up to about 10% conversion. And so experimentally what happened was we had this inlet stream of saturated hemoglobin molecules, which I will now refer to as A, dissolving into unbound hemoglobin I refer to as B, and oxygen molecules, which we refer to as C. So why does the differential reactor help us estimate these rate laws? Because we know that hemoglobin can bind to O2, we have a reverse reaction, and consequently there's equilibrium involved. So operating at a low enough conversion allows us, if we look at our rate law, to neglect particular terms. So what we can say is that the rate of hemoglobin loss minus Ra is equal to K forward times Ca raised to the alpha power. We don't know what alpha is, we don't know what K forward is. And if this wasn't a differential reactor, we would have this additional term minus Kr, the rate constant for the reverse reaction, times Cb to the beta power times Cc to the gamma power. So in this example, without using a differential reactor, we would have many unknowns and too few equations to accurately solve it. So what we end up doing is, if we keep x low enough, Cb and Cc are so low that we can essentially call them zero, so this term on the right cancels out of our equation, which makes our life easier. And this is an example of one of the assumptions that chemical engineers need to make in practice to actually get data. So figuring out what assumptions we can make early on and what are the consequences of neglecting particular terms what are the risks involved, safety risks, all these other things, and what quality of data is later on, are questions you need to keep in mind, and then you can verify it later on, or quality check what you get from it. So given this data, we're going to use a differential reactor so that we can assume that our rate law now only becomes this. So we've got two unknowns and one equation. So we need to get some more equations to accurately define Kf and alpha. And because we are working with a constant volume plug flow reactor, we first turn to a mole balance. And mole balances are the most common tools chemical engineers use. It tells us that the accumulation in a control volume, in this case our control volume is our plug flow reactor, is equal to the inlet minus the outlet plus generation. Sometimes you'll see a minus consumption term here, but we can usually lump it into the generation term. In a plug flow reactor, if we assume it's operating at steady state, any time-dependent terms become zero. It has not reached equilibrium though. That is not, steady state is not equilibrium. It's an important point you need to understand early on, but that's a topic for another discussion. And then what we need to do in the case of plug flow reactors is analyze a differential volume element, because plug flow reactors are not well mixed in the axial direction. They're well mixed, we assume that they're well mixed in the radial direction, but axially we would have concentration gradients. And because of that, what we need to do is look at a differential volume element and just take a very slight thin disk and do essentially a shell balance on this disk, where we analyze the moles of A entering and leaving and account for the reaction that is occurring in this differential volume element to arrive at a final expression. So in this case, we would have FA stands for the volume, the molar flow rate of A entering a differential element at point V, and then FA evaluated at V plus delta V refers to the molar flow rate of A exiting our volumetric, or our differential volume element. And then we have this rate of generation term, RA delta V, where delta V refers to the volume of the volume element, and then times the RA, which refers to the moles of A that react per volume per time. And so every term in this mole balance has units of moles of A per time. So doing dimensional analysis is a very important step also to make sure you're on the right track to solving any problem. It's a good checkpoint to make sure you're on the right track. And so what happens is if we take this expression and then divide it by delta V, and then take the limit as delta V goes to 0, we end up getting a derivative. We see that negative dFA, so the conventional definition of a derivative is FA evaluated at V plus delta V, and then minus FA evaluated at V. Because it's swapped, we need to have this negative sign out front, and this term here is equal to this. And then because it's equal to 0, we subtracted RA, so that's where this minus sign comes from. And further simplifying our equation, we can say that FA is equal to FA naught times 1 minus X. X refers to the conversion. And dFA, so if we differentiate both sides, would be equal to minus FA naught times dx. And then we can solve for our rate as a function of the inlet molar flow rate of A times dx dV. And so this equation is what we're going to be using to actually solve for RA up here. So now we have a second equation to use that will help us find what our forward rate constant is, as well as what order our reaction is. And we can calculate what FA naught is by multiplying the inlet concentration of A by the volumetric flow rate, which remains constant through the reactor because it's in a liquid phase, to find out what the numerical value of that is. It is important to point out here that from the data we obtained using electrodes, we were able to determine what the percent decomposition of the saturated hemoglobin was at each point along a line throughout the plug flow reactor up to a particular conversion. And the percent decomposition gives us numbers such as 1.93 and 7.48. It is very important to divide these terms by 100 because x refers to a value between 0 and 1. So if you plug in values greater than 1, you will get errors later on in your measurements or calculations when you implement the natural log functions for our derivatives. So even though the percent decomposition is 1.93, x evaluated at 0.2 would actually be 0.0193. So that was an important note. The next step, and there are multiple ways of solving these kinds of problems. If you do not have a calculator, or if you don't have a fancy computer that can calculate derivatives, what we do is something referred to as numerical integration, which is equivalent to like a Runge-Kutta series in differential equations if you've taken that class. It's essentially, we're making some approximations, so these are not 100% accurate, but they're a pretty good estimate of what the slope is of our conversion versus volume point. And so what we see is if we analyzed a control volume as it moved through our plug flow reactor, more and more of it becomes unbound as it flows through. As V increases, X also increases. So we would expect to see some kind of graph like this. And so we have to estimate what the derivative of this graph is at each point. So we'd have, and the derivative is changing over time as well, which makes, which requires us to do many calculations and to solve for our rate constants and reaction order. And so in the textbook, if you're using Folger, you can look up the ways to perform numerical integration based on the initial point, internal points, and last points. And what you end up finding is that you get different slopes for each conversion along this graph. And so now, with that data, what we can do is, if we go back and equate this expression with this minus RA term with this expression that we derived at first, we can find that FA naught times dx dv is equal to K forward times CA to the alpha power. So we know exactly what these terms are along each point of the line, and this will allow us to calculate what we want. So we create this expression here, equate the two sides, and the next step is, if we natural log both sides, it will allow us to essentially average all of our measurements to create a much more accurate approximation for what our reaction order is and our forward rate constant is, than if we just chose a single point and based our calculations from that. And so if we evaluate this, we can find that the natural log of dx dv is equal to natural log of the K forward rate constant divided by FA naught plus alpha times natural log of CA. Alpha refers to the reaction order of A, and this should remind you of an algebraic expression y equals b plus mx. And usually they're swapped, but b in this case will refer to the intercept of the line we get if we plot natural log of dx dv versus the natural log of ca. And so in Excel, what you do is you only plot the natural log of ca and the natural log of dx dv to get a line like this. And it should be linear. And if you analyze the intercept, you will find what your k forward reaction constant will be. And if you fit a trend line to the data, you will find what the slope will be, which tells you exactly what alpha is, because alpha is equal to m. Just with the intercept, you need to perform an additional calculation in which you raise it to the exponential power. So in this case, you would find your intercept value, which in this case ended up being 11.6. You would do exponent of 11.6 and then multiply that by FA naught to get what KF actually is, keeping track of the units the whole time because that is very important. And what we ended up finding was that alpha had to be equal to 1.02, which is approximately equal to 1, which tells us that the reaction order is approximately 1, first order, in this experiment. And I'd like to finish by saying performing the numerical differentiation is not necessary. A quicker way would have been to have used a computer, and if we simply plotted the conversion versus the volume that had been accumulated along the z-axis, if we plotted this in Excel and then fitted a trend line to it, we would have some kind of polynomial such as y is equal to x to the third, some constant times x to the third, plus some other constant times x squared, plus dot dot dot. If we differentiated that, we would be able to precisely figure out what dx dv is to solve for our reaction order and rate constant. And with this forward rate constant, you can pretty easily solve for the reverse rate constant, because k, the overall, the equilibrium constant, is equal to k forward divided by k reverse. So you can solve for k reverse by doing that. And the data would also be more accurate, because when we perform differentiation, we're taking infinitely many slopes along this line, whereas this we've only taken 7 points. But the reason it's important to still use numerical differentiation is because computers, especially when engineers were working on problems like these decades ago, were not as fast as they are now, which made fitting lines of best fit and a lot of other computational intensive calculations much slower and more difficult to do. So it was often found that resorting back to numerical differentiation and methods such as Runge-Kutta would be able to calculate things much more quickly despite being slightly less accurate. But again, it's another theme in engineering we see is you make assumptions and approximations within reason, and you do the best you can with what you have and hope it works at the end of the day, and there's no substitute for actually verifying the data. So in this case, if we wanted to figure out, is this reaction actually first order, we can verify that pretty well experimentally using gas chromatography to tell us exactly what the concentration of A is at a particular time. So yeah, it's always best to check the real world besides just staying in theory all day. So with that, I hope you guys found this useful. Maybe if you're working on homework 6 for reactor design class at Berkeley, this will be useful, but he'll probably change the homework next year. But yeah, thanks for watching.